In this video, I'm going to be doing the second part of Chapter 5, which deals with kinetic energy and the ideal gas laws. I'm going to be solving basic question 21, possibly basic question 22. If you want to find them, once again, just follow the link posted over here. So first of all, I'm going to be discussing the ideal gas. And the best way to talk about an ideal gas is to start with the idea of a real gas. In this case, I'm going to be using water, which is steam. And the reason I'm going to be using water is because it has a lot of properties that make it different from an ideal gas. The first of these properties is the existing forces between water molecules. As I'm sure most of you know, when you have two water molecules, the hydrogen of one molecule will always attract the oxygen of another, causing a hydrogen bond to form. This bond isn't important for this chapter. You don't need to worry about it for chapter 5. But all you do need to know is that it does exist, as do electric forces, because the molecule is made of protons and electrons. And all these forces aren't very important. All we need to know is that they just affect how the general molecule behaves. The second thing you need to know is that whenever two gas atoms collide, just like you would expect them to, they will collide and then bounce back off of each other. But because they lose heat, they lose energy, they need to use this energy to move away from each other, there is always going to be a loss of energy for every collision. This is not new information, we already know this. It's just important to understand the concept of an ideal gas. The second thing I'm going to discuss is the mass and volume of every individual H2O molecule. When we look at it, it's very clear that H2O has mass. We can find it using the periodic table. It's 18 grams. And of course, every H2O molecule, which is drawn like this, takes up a certain volume, which is, how it causes pressure, how it interacts with everything. This is just something that a molecule has to have. It has to have mass and volume. The third thing I would like to mention is a change in conditions. H2O, which is obviously steam, only exists if the temperature exceeds 100 degrees Celsius. If the temperature falls below 100 degrees Celsius, then as we all know, H2O is going to condense and become regular water. The second thing we need to remember is that if pressure increases, if I have this massive box of steam and I put all the steam in a smaller box like this one, then once again it will condense because that's simply how water behaves. The molecules will get closer to each other, they're going to attract each other more, and eventually they're going to stop behaving like gases. And the last thing we need to remember is the gas laws. Of course, we can use the gas laws for virtually any gas, and they will always be correct. But one thing we need to remember is that the gas laws are not always accurate. They only apply under certain conditions. For example, if we look at the law V1 over T1 is equal to V2 over D2, especially in the case of water, we quickly realize that if either of our temperatures is below 100, then it's going to stop being a gas. And once it stops being a gas, then we can't use the law anymore. This isn't new information. This is just how water behaves. This is how many gases behave. They condense, they have mass, they collide, they exert forces. And this is important for understanding why we need the concept of an ideal gas. So now if we go back to an ideal gas, the importance of an ideal gas lies in the fact that all of these issues that affect how something like water behaves, they don't exist in an ideal gas. An ideal gas isn't actually real. It cannot be found in nature. However, the reason we talk about it is because it will perfectly follow each gas law and it will have none of the problems that real gases have. For example, a real gas would have volume. Volume is present. And let me rewrite that because it's not very clear. It will have volume and the volume exists. And because the volume exists, each molecule will exert forces on each other, whether they would be the hydrogen bond that you get in water or just an electric force because of the interaction of the protons and electrons. The forces just exist and so does the volume. But when we're talking about an ideal gas, which has to perfectly follow every single gas law, these laws would be affected because of these forces. For example, the forces of water would come into play when the temperature reaches below 100, and we don't want that. So in an ideal gas, the volume is negligible for each molecule. And the forces do not affect the gases. The gases exert no forces on, the gas atoms, I should say, exert no force on each other. The second thing we want to look at is motion and collisions. As we've established with a real gas, real gases move around, and when they collide, there's always going to be a loss in energy. And this is just because the energy is lost to heat or to keeping the gas moving. It's nothing new. But in an ideal gas, once again, if the gas loses energy, then it's going to affect how the gas works, and we don't want that. So the collisions in ideal gases are always perfectly elastic. And what this means is that there is no loss in KE, kinetic energy. The third thing we want to look at is what I just mentioned, which is kinetic energy, which also ties into the gas laws. And it's the fact that in real gases, while the relation kinetic energy with temperature does apply, again, it stops being accurate once you reach a certain point. If the temperature is too low, then the gas won't be a gas anymore. It'll be a liquid, and it won't apply anymore. So this relation applies, but is not exact. And the same can be said for all the gas laws. While they do apply, once you reach a certain point and the gas becomes a liquid or a solid, they're going to stop applying, so they're not exact. In an ideal gas, we solve this problem by saying that the gas laws apply at all times, and so does kinetic energy. Kinetic energy over here will always be proportional to the absolute temperature. The gas laws here will always apply. There's going to be no such thing as a gas becoming a liquid and the laws becoming null. And this carries perfectly into the last point, which is that a change in conditions for a real gas will make them stop being gases. They're going to condense. But because an ideal gas follows all these laws perfectly, it's never going to condense. Not even if you take the temperature to be negative, not even if you make the temperature 0. It will always be a gas no matter what. And once you look at all these things, we can see why we have certain conditions in which we try to have ideal gases. Now, of course, as we did say, the ideal gas can't be found in nature. It doesn't exist. But to test all our formulas, we do need to use some sort of gas that copies it. Usually, people use hydrogen. And the reason we use hydrogen is because, let me just write this here, conditions to mimic ideal gases, not to actually create one because it's not real. The conditions are we use hydrogen because it's very light, and that means there's going to be very, very few forces interacting. And we always keep the temperature very high to prevent the gas from condensing. And for the same reason, we always try to keep the pressure very, very low. This is never going to give us an ideal gas, but it's good because this is the closest we could get to an ideal gas. And this is what we use to test all of these formulas that we have. So from this, you should also remember that the gases that deviate the most from ideal behavior, the gases that cannot do this at all, are always the heavy ones, stuff like SO2 or HCl, where the gases are really heavy and there's all these forces between them, and they can't exhibit this behavior. Something like hydrogen, which is very, very small and very light, can get close to this behavior because the forces aren't there, the temperature is kept high, the pressure is kept low. So you should keep this in mind whenever you receive any question about the conditions of ideal behavior. I'm now going to move on from this and talk about kinetic energy. And as I'm sure you know, kinetic energy is thus any energy caused by the motion of an object. In this case, we're talking about gases, and the equation for kinetic energy is one that we're all familiar with. It's half mv squared. Now, when it comes to gases, we should always remember that kinetic energy is directly proportional to the absolute temperature. Once again, absolute means Kelvin, which for Celsius you add 273, And the other thing we need to know is that at the same temperature, the Ke, kinetic energy, stays constant and the same. Any two gases at the same temperature, if we have oxygen and hydrogen at the same temperature, they're both going to have the same kinetic energy. From these two facts, we can get these two formulas over here. This formula just means that at the same temperature, the kinetic energy of the first gas is equal to the kinetic energy of the second gas. And this formula over here is a rewrite of the first one that we have, which states that molar mass 1 over molar mass 2 over the second molar mass gives you the velocity of the second one. Remember this, it's 1 over 2, 2 over 1 over the velocity of the first. We usually use these in questions where the kinetic energy of two gases is the same. And to test out these formulas, I'm going to be solving basic question 21 over here. So basic question 21, it states that we have the two gases hydrogen and this gas over here, which I'm just going to be calling our mystery gas. The mystery gas diffuses 4 times slower than hydrogen, and they want us to find the molar mass of it. So to start, we should start with our given. We know the molar mass of hydrogen, which is 2. This is just straight from the periodic table. The molar mass of the mystery gas, NX2H2X, is what we're trying to find. And while we don't have the velocities, we do have a relationship between them. We know that the second gas moves 4 times slower than hydrogen. So getting this relation down is the most important part of getting this question right. If you don't get this right from the beginning, you're not going to be able to solve the question. So the way I like to think of it is that whatever the velocity of hydrogen is the bigger velocity. And we know it's bigger because the question literally tells us that. It tells us that this one is slower than hydrogen. Hydrogen is the bigger one. And since it's the bigger one, it makes sense that if we have the velocity of the mystery gas, we're going to have to multiply it to reach hydrogen. When you have a smaller number, you always have to multiply it to reach the larger number. That's just how maths works. If you guys want another way to think of it, just always think that the multiple will go around the slower gas or the heavier gas. That's another way you can think of it. But the point is, you have to get this relationship right, because once you get it right, the entire question becomes very, very easy to solve. And yeah, once again, since this one has a smaller velocity, it makes sense that you have to multiply this one by 4 instead of the other way around. So now that I have all my values down, all I'm going to do is just substitute. I'm going to be using this relation. Half m1 v1 squared is equal to half m2 v2 squared. I'm going to cancel half on both sides just to make it easier for myself. The mass of hydrogen is 2. The velocity of hydrogen is just the velocity of hydrogen. The mass of this is what we're trying to find, so I'm going to keep it as it is. And the velocity of our mystery gas is again just the velocity of the mystery gas. Now we can just substitute either of these two based on the relation we have here. I'm going to be substituting in here. So 2 times 4, 2 times 4 times the velocity of NXH2X, all of it squared, is equal to the mass we're trying to find times the velocity, again, of NXH2X squared. Once you square across, you're going to get the 2 times 16 times the velocity of the gas squared is equal to the mass we're trying to find times the velocity of the gas squared. You can cancel this variable on both sides. You're going to end up with the mass being 32 grams per mole. I really hope that was clear. Once again, just keep in mind the relationship between the velocities is the most important part. You need to get this right before you can start solving. I'm now going to move on and solve basic question 22. Basic question 22 tells us that we have 5 milliliters of oxygen and 5 milliliters of gas X. This 5 milliliters is just here to confuse us. It's irrelevant to the question. Oxygen requires 50 seconds to effuse, and under the same condition, gas X requires 80 seconds to effuse. Similarly to question 21, they want us to find the molecular mass of gas X. For this question, I'm going to be using the second formula. Let me write that neater. m1 over m2 under the radical is equal to v2 over v1. I'm going to rewrite this so it fits my gases that I want. The mass of oxygen over the mass of X is equal to the velocity of X over the velocity of oxygen. And then I'll write down my given. The mass of oxygen from the periodic table is 32 grams per mole. The mass of X is what we're trying to find. And the velocities we don't have. What we do have is the time, 50 seconds for oxygen and 80 seconds for X. Now, this might seem like a question that we need a completely new formula to solve, but we don't. If you guys remember from physics class, velocity is equal to the displacement traveled over the time. Now, we've been told that this is the same conditions. The same conditions implies that they have effused the same distance, which means that this X right here, this displacement, is the same for both gases. Going off of this, we can say that the velocity of oxygen is equal to the displacement it traveled over the time, which is 50 for oxygen, and that the velocity of X is equal to the same displacement over the time it took, which is 80 seconds. And now that we have both of these two, all we need to do is just substitute up here. The mass of oxygen, which is 32, over what we're trying to find, is equal to the velocity of X over the velocity of oxygen. You can cancel X, and if you guys just input this value over here in a calculator to make it easier for you, you're going to get 32 over what we're trying to find is equal to 50 over 80. From here, it's just a matter of cross-multiplying, and the mass of X that you get should be something around 81.9, which rounds to 82 grams per mole. I really hope that was clear. Like I said, for this question, you just have to remember that this relation exists. If you do want to remember a formula that doesn't involve all of this deriving, just remember that when you have mass 1 over mass 2, unlike the velocity where we switch them, for the time we just keep them the same. And that's all you need to know. Thank you guys so much for watching. I hope this was clear. And as I said, there will be another video going over the harder questions in this chapter. And that's it. Thank you for watching.